we are working our way through section 5. In the last lecture, we introduced the idea of this general derivative, so a vector-valued function of many variables and its derivative. And in that context, we introduced the idea of the Jacobian matrix and differentiability, and also the determinant of this Jacobian matrix, which is going to be very important when you move on to double and triple integrals. So you'll come back to the idea of the determinant of the Jacobian matrix. In this lecture, we are going to finish this section. We're going to look at some other ideas involving this general Jacobian matrix. In particular, we're going to look at the chain rule and another idea called the inverse function theorem. So if this Jacobian is kind of like a matrix, a derivative in a matrix setting, what can we do with it? Well, what sort of ideas do we know from calculus? One of them is the chain rule, and the other one, which you would have seen in Math 1131, is the inverse function theorem at a very sort of basic level. So that's what we're going to look at today. Okay, so the chain rule. Suppose we have two of these vector-valued functions of many variables. We have some mapping which maps the vector x to g of x, and then f acts on that g of x. Now, the technical way of writing this composition is f of g of x, or fog x. Before we actually tackle the chain rule, let's look at how we compose these really general functions, the composition of these general functions. So suppose we have g and f defined here and here. How would we define the composition f of g? Well, it's very similar to what you would expect if we're taking, I guess these should be a boldface. If I want to take f of g of x, y, where this is a vector, well, all I do is I take these components, write them in here, and then I move over to my f, I replace whatever's here, whatever's here and here, here and here, and just multiply the two things. So this times this. That's what we get down here. Okay, so it's the same composition of functions that you would expect, but it's just a little bit more abstract because we're working in these sort of higher dimensional settings. All right, so let's talk about the chain rule. The chain rule is all about differentiating composition of functions. If the Jacobian matrix is some sort of general derivative, what can we do with the Jacobian matrix in the environment of the chain rule? Well, I'm glad you asked. Now, throughout this section, if we've got a function, a vector-valued function g, then this is going to pop up all the time. Now, if our functions, f and g, are differentiable, then the Jacobian of g at p and the Jacobian of f at b are well defined because they're differentiable. Well, we can formulate the following chain rule. So suppose G maps this set into this set, F maps this into this, and suppose they're both differentiable. Remember, we talked about differentiability last week. If a function has continuous partials, or all the elements of its Jacobian are continuous, then it's differentiable, okay? Well, under these conditions, the following is the chain rule. It says that the Jacobian of the composition is equal to the product of these two Jacobian matrices. Okay, and just remember the subscript's just where you're evaluating each Jacobian matrix. So this is pretty much what you've seen at school or in first year, but the difference is we're using possibly matrix multiplication. Okay, so you're possibly multiplying two matrices over here. They might be, they might be vectors as well. This might be a dot product over here. And we'll have a look at that in a minute too. So just to recap, the Jacobian of the composition is just the product of the two Jacobians. Okay, J of F and J of G. That's all it is. So let's have a look at this in action. I'm not going to prove it, okay? But here's an example based on the functions introduced in example 5. So here we've got G and F defined in the following way. What we're going to do is just verify the chain rule. So essentially what we're going to do, we're going to work out the left-hand side, we're going to work out both of these parts of the right-hand side, multiply on the right and show that they're actually equal. Okay? Okay, so if this is our G, then we can calculate the Jacobian. Remember, the Jacobian is just the matrix where the rows are derived by using the gradient. Okay? The gradient of each component function. Okay, so this is our Jacobian of G, where P's this. If I work out the Jacobian of F, well, again, just go through and calculate the derivatives that you want. Now, this is evaluated at G of P, so A1, A2 goes in here, and that's how you get these two points. Okay, so if you sub in for X, sub in for Y, you'll get the following. Okay? So that's kind of the right-hand side of this. All we've got to do is sort of multiply them together and then compare it with that. Now, from our earlier example, we computed fog, and you can then compute the Jacobian, and you'll get this. And then if I multiply, so evaluating this at P, you notice that this is just this matrix times this matrix. So what we're doing here is just kind of confirming that this bottom chain rule really holds. So this actually is equal to, so this is the left-hand side, and this is the product of the right-hand side. Okay, so I'm not going to prove the chain rule. What we are mainly interested in is the application of the chain rule. So we want to appreciate it, and we want to be able to use it to, I guess, give us an understanding of what we already know with the chain rule, but also you want to be able to differentiate and find Jacobians in this setting. How does this general chain rule compare with what we already know? So, at school, you learn about the chain rule in first semester, first year. Earlier in this course, we were looking at all sorts of chain rules. Okay, we draw the little linking diagram to get all the parts of the chain rule. Well, what I've just presented to you is a general case of these earlier chain rules that we've seen. So let's really break it down. Functions of one variable. So x is a differentiable function of t, u is a differentiable function of u, then the composition is given by this. Now, in the notation of this section, if you wanted to calculate the derivative with respect to t, that's just the Jacobian. So on the left-hand side, I've got this. And on the right-hand side, well, this is just du dx, and this is just dx dt. Okay, so what we usually write this when we're sort of learning calculus, this is sort of how we write it. Okay, and we're sort of implicitly assuming that u is a function of x here and x is a function of t. Now, what about something a little bit more closer to home in this course? Just suppose, I've got this function f of two variables. It's a real valued function. Okay, it's the kind of functions that we were looking at in section 2 and section 3. In particular, each of these variables, x and y, depend on, say, one variable, t. Now, in the notation of this chapter, or this section, boldface x would represent the following vector. And if I wanted to differentiate f with respect to t, then that's just the left-hand side here. And the right-hand side, again, are just special derivative type things. So this, you can think of this like a gradient, and this is just, I guess the vector dx dt. Notice how they're multiplied together. We've got sort of a vector, I guess a column vector, a row vector multiplying with a column vector there in some sort of dot product. Okay, so basically this and this are the same, but this is just written in this Jacobian type notation, whereas this might look a little bit familiar, more familiar. So if I expand this out, what do I get? Now that's got to look familiar, right? That looks familiar. That's right. So can you see now? You could sit there and go, hang on, Chris, what you were telling me when we learned about the chain rule in section 2 was all a bunch of hooey. I don't have to draw a linking diagram and go from the top to the bottom. Well, yeah, you can just think of it as two sort of matrices multiplying together. It's another way of looking at it. Okay? Just another way of looking at it. It's up to you how you want to remember it. Okay, so this is just what we saw in earlier sections. So the chain rule for the Jacobian makes perfect sense and is a more general case than what we've already been looking at in the sense of a chain rule. Is everything all right? Okay, no worries. It's okay. Now, the second part of this lecture. The chain rule is really not that hard. As long as you can get on top of the notation and the Jacobian type of notation, it's really not that difficult. This is a little bit more challenging. And one of the reasons is, I believe, that students don't really understand or they don't even recognise that they've seen this already in first year. Okay, it's called the inverse function theorem. The inverse function theorem. So suppose you've got a function, a real valued function, and its derivative at some point is not 0. The inverse function theorem says that under that condition, that underlined condition, f has an inverse, that inverse function's differentiable. I guess as long as we're not too far away from f of a. And you can compute the derivative of the inverse function at this point just by taking the derivative of f at the point and, dividing it into 1. Now, Here's a good test. Who actually remembers that from Math 1131? Yeah, see? That's my point. So it doesn't matter. If you don't know anything about this, that's okay. You can learn it now. Okay? Very powerful theorem, and we're going to build on that today. So if you don't know this theorem, don't worry about it. Just imagine you're learning this for the first time. This kind of theorem is called an existence theorem. It tells you, under certain sufficient conditions, there is an inverse function that exists with the following properties of its derivative. Okay, it's an existence theorem. Very powerful ideas. Now, if we're playing around with all these general functions, what happens in this so-called multivariable case? Do we still have this true for, say, partial derivatives? Well, the answer is no, but if I change these to Jacobians, so you've got like a general Jacobian type derivative, Jacobian matrix, we can build on this. So hopefully this gives you the idea now. Why did we define the Jacobian the way we did? It seems very strange. Well, one of the reasons is because it does what we want it to do. Okay? In maths, we get judged by what works rather than what doesn't work. So when you're defining something or you're introducing something for the first time, you want it to do certain things. So you define it in a way, many times, so that it will do exactly what you want it to do. Sneaky, huh? Okay, so let's just look at a simple example. Just suppose, I've got a function defined in the following way. So the top line can just be written like this with this function f. And the second line below it, just this one here, this is like the inverse. So here we've just rearranged everything. We've calculated the inverse. And we can explicitly write down the inverse. Once we know f, we can write down the inverse function. Now, if we differentiate, so let's say we just calculate a few partials. Here I've calculated dr dx and dx dr. I get this and this. And I see that, well, dr dx isn't equal to 1 on dx dr. So the thing to remember there is that, well, this inverse function theorem isn't going to work if we just stick to partial derivatives. Okay? But if we use the Jacobian, maybe things are a little bit different. Okay, so if we use the Jacobian matrix, then there is a generalization. Okay, so suppose we've got our polar coordinate example again, and our inverse function. Sometimes it's denoted by G. It just saves a little bit of a few headaches in notation. Now, what do I know about inverses, functions and their inverse? Well, if I compose f with g, or g with f, what do I get? Well, I get the identity. Okay, so basically f and g undo each other, and you're just left with this column vector. So by this ID, I just mean, the mapping that sends the vector xy to xy. That's all it is. Okay, similarly, if you compose it the other way, you get the identity. Okay, well, if I've got this identity, I can compute the Jacobian, and it's just the identity matrix, right? Which we sometimes just write as I. So don't confuse this is an I times D here, just short for identity. And this is the identity matrix that we meet in first year. Okay, so where is this going? Well, if I now apply the chain rule, I get the following. The Jacobian, and now remember, G is just F inverse here. Okay, so G is F inverse. If I look at the product of these two Jacobians, it's the Jacobian of the identity, right? Which is just the identity matrix. And, you know, I guess vice versa, if you switch the matrix multiplication around the other way. So what does this mean? If I have two matrices and I multiply them together and they give me the identity matrix, what does that mean? Well, it means that they've got to be inverses, right? They've got to be inverse matrices. That's how we define an inverse matrix. So what does it mean? It means that this is the inverse of this, and vice versa. Yeah. So what? What it means is that if you want to compute, remember this is just the Jacobian of F inverse. Let's say you've got an F and you want to compute the Jacobian of its inverse. Well, all you do is you compute the Jacobian of F and invert it. That's pretty good. From a computational point of view, that's pretty good. Okay, so here it is written out for our polar coordinates. Okay, you can check it, and the idea works in general. Now, this is it. The inverse function theorem. Suppose I have a vector valued function, this time mapping Rn to Rn, and it's differentiable at some point in its domain. If the Jacobian of F is invertible, an invertible matrix, then F has an inverse function defined in some neighbourhood of this point. And in particular, I can calculate the Jacobian of that inverse function at this point just by taking the Jacobian of F and inverting the matrix. Okay? So the first part is like an existence thing. It says the inverse exists as long as you're close to the point of interest. And the last line is a computational thing. It'll help you compute the Jacobian of F inverse, or the inverse function. Okay, so there's sort of two bits to it. Okay, when I say some neighbourhood of this, I mean, you know, you've kind of got like a little open disk around the point, and it may only exist around that, in that little disk. Okay, so this is huge. This theorem's phenomenal. You may not appreciate it at 5:30 on a Monday afternoon, but that's okay. You'll warm to it. I can tell. This is an amazing theorem. So let's look at that work. How does it work? Okay, well, here's an example that I've created earlier. Again, back to our polar coordinates example, I can calculate the Jacobian matrix. The next question is, if I want to apply this inverse function theorem, well, is this matrix invertible? Well, how do we determine whether a matrix is invertible or not? Look at its determinant, right? If it's got a non-zero determinant, then the matrix is invertible. Yeah. So let's look at the determinant here. It's R. So it follows that this is invertible as long as we're excluding the point r equals 0. And we can apply the inverse function theorem, so we know that f has an inverse, so denoted here by G, and that inverse function's differentiable. So that's a kind of one that I prepared earlier to sort of step you through it. Essentially, what your job here to do is, when you're applying this theorem, is just tick off that the assumptions of the theorem are satisfied in a systematic way. Now, lastly, you might remember this notation from the previous lecture, just the determinant of the Jacobian. You can apply the chain rule to these determinants and come up with the following. If these two matrices are inverse matrices, then you know that if you multiply their two determinants together, you'll get 1. Now that boxed equation might not seem like very much, but when you look at double integrals and change of coordinates, it's going to be really important.